Good afternoon, class. It's Sir Capistrano again, and welcome back to another lecture for our class, Chem 21, Organic Chemistry. Wherein today we will be talking about the effects of substituents on electrophilic aromatic substitution. So, by electrophilic aromatic substitution, what we mean here is we will be talking about generally, we will be talking about benzene, and benzene being an aromatic compound, which means benzene has six carbon atoms in a cyclic analog, wherein we have an alternating double bonds across those six carbon atoms. So by electrophilic aromatic substitution, it's just mean that we will be substituting electrophiles uh, substituting electrophiles to the hydrogen that is present in our benzene. That's why we call it electrophilic aromatic substitution. So basically, let me just give you some background regarding our aromatic compounds. And by aromatic compounds, it just means that these compounds are cyclic planar compounds. And as you can see on the moving image earlier in the title, uh, planar, it means all of the atoms in the benzene ring is actually located or placed on the same plane. Na parang isang sheet lang, dun sa isang sheet na yon, nandun yung anim na carbon at yung anim na hydrogen. So these compounds contain a six carbon cyclic analog with alternating double bonds, what we call benzene ring. So when we talk about aromatic compounds, these compounds have benzene ring. And the most basic structure is a benzene, which can be written this way. We have three figures here that represents benzene. So we have here the first one with a hexagon with a circle inside it. We have here an hexagon structure with alternating double bonds. And we have here this expanded or hindi yung shortened version ng pagsusulat natin wherein we see here that we write the six carbons, the three double bonds, and also our hydrogen. So some of you may be thinking, sir, why do we need to use that circle? So basically, when we talk about benzene, if we have that hexagon shape, as you can see here, as you may see here, uh, the double bond is not limited in this orientation. We can still write our benzene ring in a way like this. So meaning to say, these two are actually resonant structures of each other. So as long as the bonds or the double bonds are alternating within six carbon cyclic analog, it still is a benzene ring. Meaning to say, uh, kaya tayo gumamit ng circle, hindi stricted or hindi restricted yung movement or yung position ng ating mga double bonds. Okay? So that is why we use that figure with a hexagon and a circle inside it. Okay? So let's go or let me show you an example of what we call electrophilic aromatic substitution. So I have here class nitration of benzene. Meaning to say we will be adding nitrates or NO3 or NO2 on our benzene. And by substitution or electrophilic aromatic substitution, if we have here this benzene, which is actually an aromatic hydrocarbon, we will be substituting the NO2 to that hydrogen that is connected here. So this nitration only happen in the presence of our sulfuric acid in 50 degrees Celsius. So we have here our nitrobenzene. So basically, when we talk about, as we see here, there are actually six, there is another five hydrogens that we can substitute here in our nitrobenzene. So if we proceed on our nitration of nitrobenzene, or we will be adding or further nitration of our benzene, we will be having this scenario wherein instead of just one product, we will be actually having these three products. So as you can see here, we have this is the original substituent of our first nitration. And as you can see here, the nitrate actually bonded to different sides of our benzene ring. And upon measuring how much of each of the product may be contained in this reaction, after adding more nitric acid and sulfuric acid and our nitrobenzene is put into a temperature which is 100 degrees, we will actually have here 1,3-dinitrobenzene, we have here 1,2-dinitrobenzene, and we have here 1,4-dinitrobenzene. Wherein, if we set or we look into the locations, as we can see here, we have here 1, 2, 3, that is why 3, 1,3-dinitrobenzene, and we have here 1, 2, that is 1, 2, because the nitro is attached to the second carbon, and we have here 1, 2, 3, 4 for this one, and because the other nitro is attached to the fourth carbon. But going back to the proportions, if we measure how much 1,3-dinitro, 1,2-dinitrobenzene, and 1,4-dinitrobenzene in our reaction, we will actually measure that we have for our products, we have 93.2% of the product will be 1,3-dinitrobenzene, and we will have here 6.4% will be 1,2-dinitrobenzene, and we will have 0.3% for our 1,4-dinitrobenzene. So, what then? But if we look into another example of electrophilic aromatic substitution, let's have here our toluene. By toluene, this is just benzene with a metal group attached to it. If we conduct nitration of this aromatic compound, which is toluene, as you can see here, again, we will be having three different products wherein we have one methyl 3-nitrobenzene, and we will have here 1-methyl-2-nitrobenzene, and lastly we will have here 1-methyl-4-nitrobenzene. Again, all of them are located in a certain position wherein we have here 3, we have here 2, and we have here 4. But you may expect na parehas yung reaction. So, ang mangyayari, karamihan siguro ulit ng product ay nandun ulit sa 3-nitro or dun sa third position of our carbon. But, if we actually look into the proportions of these products, you may notice or you may measure that we only have 5% for the 1-methyl-3-nitrobenzene. We will have 62% for our 1-methyl-2-nitrobenzene. And lastly, we will have 33% of our product will be 1-methyl-4-nitrobenzene. So why is that? So basically, as we can show here in our example, there will actually be a certain position or a certain orientation wherein our electrophiles or our electrophilic addition on mono-substituted benzene we will notice that the first substituent determine the reactivity of the orientation and the orientation of the new electrophilic substituent. So the already attached substituent determine whether most of the new substituent will be attached to the meta, ortho, para, or aroma or ortho meta, ortho, or para orientation of the aromatic compound. So by ortho, it's just a Greek word for similar, wherein our non-hydrogen substituents will be attached at 1 and 2 positions of the aromatic compound. We have here meta, which is only a Greek word for following. We will have here non-hydrogen substituents will be positioned at 1, 3 positions of the aromatic compound, and para, which means similar in Greek. So non-hydrogen substituents will be attached at 1, 4 positions of the aromatic compound. So it just means that kapag meron na tayong naunang naka-attach or we initially have a substituent for our benzene, that the presence or the existence of that substituent will affect the new substituent kung saan siya mag-attach. Kumbaga, kung balikan natin yung examples natin, dito sa example na to, since we already have our NO2, it affected or the next nitration favors what we call the meta position. So this is meta, this is ortho, and this is para. Meta because it follows or the next it will be attached to the next double bond position. Ortho because they are in the similar on the straight or correct double bond, and para for similar, they are both on the same orientation. So as you can see here, our NO2 actually favors what we call the uh, meta position, wherein it is located on the third carbon, or our substituents will be attached to the 1 in 3 position. So uh, in that, let's look into the further or the nitration of another hydrocarbon. So as we can see here, due to the presence of the metal substituents, the nitration actually favors what the ortho position and the para position more than our meta position. So as you can see here, class, uh, we will have here that we actually may notice here that the electrophilic attacks or yung pag-attach ng ating electrophile dun sa monosubstituted nating aromatic compound ay magde-determine nung tinatawag nating reactivity kung saan mangyayari yung attack. Therefore, yun yung magdidikta or magsasabi ng tinatawag nating posisyon. Whether magiging meta ba siya. By meta, it is located in the 1-3 or the substituent will be located at the 1-3. Ortho, wherein the substituents will be attached to the 1-2 position, or para, wherein our substituents will be attached to the 1-4 position. So in that, actually, we have, due to that, para malaman natin or ma-predict natin kung ano ba yung magiging major product ng ating mga reactions. So as you can see here, on our further nitration of nitrobenzene, our major product will be our 1,3-dinitrobenzene. And for the nitration of toluene, as you can see here, the major product will be ortho, or the 1-methyl-2-nitrobenzene, and next yung ating para or yung ating 1-methyl-4-nitrobenzene. So para talaga. So to be able to determine or predict the major product of the reaction involving our electrophilic aromatic substitution, we can actually characterize our substituent groups. By substituent groups, ito yung mga pwedeng or yung mga electrophiles na pwedeng mag-attach dun sa ating aromatic group. So bakit ba natin pala sila kino-consider lahat as electrophiles? So as you can see here, based on our structure of our benzene, there's actually a lot of electrons present in our aromatic group. That's why any reactions that may be attached or may be involved to benzene, we consider that as an electrophilic attack because those substituent that will be attaching to our aromatic group has lesser electrons, meaning they tend to be the electrophile rather than the nucleophile, wherein our benzene ring is actually our nucleophile. So, in that, let's go to the classifications of our substituent groups. So, we actually have two major classes of substituents, but we have a special group wherein we have here our halogens, where these halogens are the activating OrtoPara directors. But the major classes of these substituents are the activating OrtoPara directors, and we have here the deactivating meta directors. So for the examples or for the substituents that are activating and orthopara directors, we have this substituents. So I arrange, or this is arranged actually regarding on how they are strong activators. So we have strong active orthopara directors. We have the hydroxyl, the ammonium, the amines, and the amide or the tertiary amide. And we have the moderate, wherein we have our what this OR groups, wherein R is actually our alkyl or aryl group, and we also have this acetamide or this amide. This is a moderate activator of para, and we have weak activators here, the benzene ring itself. Alright. And our alkyl group. So we have here our aryl and our alkyl. So these are the activating paradirectors. So as you may have remembered on our example, we have our toluene, wherein our toluene is actually just a methyl compound, and that metal will actually fall under the weak uh, octo ortho paradirectors because it is an alkyl compound. So if you have uh, your benzene ring, then there's another benzene ring that is attached to it. This will, ang mangyayari dito class, it will be an activating orthopara director. So if you add another substituent into this, that substituent will actually attach to this ortho side or this side. Pero kung ang titingnan natin ay itong isang benzene, dito mag-a-attach yung ano, ganun din. We will have here that this is the sites wherein our substituents will attach into. Okay? Same with our toluene here, as you may have remembered, we have our major product is attached to this second carbon, and lastly we have here this attached into our para orientation. Okay. And also we have the deactivating meta directors. So we have here our NO2 earlier. We also have this amine. We also have this cyano, okay? And we also have this carboxylic acid. Uh, and we also have here our, what do you call this? That one, COR, where in R is again the alkyl group. Nakalimutan ko na kung ano siya. And we also have here our SO3H. Also, we have here our formyl group. By formyl group, we have here this acetaldehyde nga ba ito. And we also have our ketone here because of the R, which is actually another alkyl group. Okay? Meaning to say, like just like our NO2 earlier, if you have a benzene ring and you have any of these meta directors, say if we ano dyan, we write is that as M or meta directors, and we have here our benzene. Once we added another substituent, that substituent will be attached to this meta side or our 1,3 position. Okay? And lastly, we have our halogens, wherein halogens are the activating OrtoPara directors. So we have here our fluorine, bromine, and iodine. So meaning to say, if we have a benzene ring here, and our halogen is attached to this side, since this is OrtoPara directors, most of our products will be attached to this side or to this side. So baka nalilito yung iba class, pwede mo ring ortho yung kabilang side. So either of those sides of our halogen can be an ortho side or ortho orientation. Okay, so that is our three substituent groups for in electrophilic aromatic substitution. So we have here the activating or orthopara directors. We have here our deactivating meta directors. We also have our deactivating orthopara directors, which are actually our hydrogen. So paulit-ulit yung naririnig, ano? Activating, deactivating. So, ano bang ibig sabihin nun? So, in that, let's talk about kung ano yung sinasabi nating activating or deactivating. So, when we talk of why activating and or deactivating, this actually falls under the theory of reactivity and orientation, wherein we will be talking about the resonance structure of our benzene or aromatic compound. So, I have here two aromatic compounds. We have here the aniline and we have here our benzaldehyde. So for our aniline and benzaldehyde, as kapag i-review natin, ano, actually, our NH2 is deactivating or activating OrtoPara director. And as you can see here, our aldehyde group here is actually a weak, yung ating CHO is actually deactivating meta director. So ano ba yung difference ng dalawang yan? So when we talk of activating orthopara directors, ang nangyayari dito class, meron kasing tendency yung ating activating orthopara directors just like our NH2 to release what we call what may tendency silang mag-release ng electrons. So as you may have remembered, if you go back to our Lewis structure of our nitrogen, it has actually some lone pairs. And ang nangyayari, pag meron tayong lone pairs, due to the stability or due to the pull of our benzene ring dun sa ating sa ating mga electrons, it may have a tendency that this electron will be migrated to the carbon and nitrogen bond or kahit anumang bond na existing na magpe-pair up. And one of this ring or one of these bonds in our ring may be actually moving to that side. Meaning to say, we will have here an excess negative charge. So, ang mangyayari dito, magkakaroon tayo ng double bond dito sa taas, double bond about our nitrogen, wherein it will be positively charged due to the missing electron. And this side, dahil dun sa nawalang ka-double bond ng bond dito sa ating side na ito, we will have here a negatively charged benzene ring, and andun pa rin yung ating mga double bonds. And due to sabi ko nga sa inyo kanina, due to the resonance structure of benzene ring, that negative charge may move around our benzene ring, wherein from here, if you have an excess electron here, that electron may move to that double bond, therefore breaking that bond. So magkakaroon tayo ng ganitong structure wherein magma-migrate yung isang electron towards dito, making this side negative, and still andun pa rin yung ating positively charged na nitrogen. Same goes here. So pwedeng yung ating instead pala, o baliktad pala class, due to the presence of nitrogen here, one of the electrons here, one of the electrons may move to this side, to this bond, and will pair up with this lone electron. So, kaya tayo nagkaroon ng negative dito. And same goes here. One of the electrons of this side may be attracted to that electron, therefore forming a bond. So, magkakaroon tayo ng bond dito. And bond dito. And malilipat yung negative charge natin dito. Tapos, pwede rin siyang mag-resonate pabalik din sa ating first structure, which is aniline. Then, bigla kang mapapaisip, so what, sir? Bakit? Ano naman kung nagiging ganyan yung structure? Ano kung bakit meron anong sense naman kung bakit tayo nagkakaroon ng ganyang structure? Or ano namang may itulong niyan dun sa understanding natin bakit siya activating or bakit siya activating OrtoPara director. So as you can see here, class, tingnan nyo yung locations ng ating negative bond. Not negative bond, negative charge. Of all of these locations are actually ortho and para orientation. So basically, if you have a substituent that is considered to be activating, or by activating, it can let go or release electrons towards the benzene ring. Anong nangyayari? I-activate niya lahat ng ortho and para directions or para orientations. So, yun yung sinasabi natin by activate, nagkakaroon actually tayo ng negative side dyan or negative charge. And as you may have remembered, we were talking about electrophilic aromatic substitution. So, by electrophilic, our substituents are actually looking for an excess electron. And each of those negative charge are actually sites or electrons. So, meaning to say, those are sites for bonding. So as you can see here, as pag sinabi nating activating OrtoPara direction, ang nangyayari, the tendency or due to the releasing of releasing of that electron from the substituent, nagkakaroon ng activating sa ortho and para direction more than activating nung sa ating meta. So, ganun yung nangyayari. Dahil mas nag-activate yung ortho and para orientations natin around dun sa ating benzene ring, mas favor or mas nagiging bonding site yung ating ortho and para directions rather than meta orientation. So, the opposite is the same for, the opposite is true about our deactivating meta directors. So, ano ba ang nangyayari dun sa activating? So, ano nangyayari? Instead of the group or instead of the substituents providing excess electrons toward the benzene ring, baliktad yung nangyayari. Kumukuha siya ng kumukuha siya actually ng tinatawag nating electron. So what happens here is one of the bonds or one of the electrons in this double bond between our deactivating meta director will be moving towards the further side of our substituents. Meaning to say, magkakaroon tayo ng tendency na yung isa dun sa mga double bond within dun sa benzene ring natin ay mawi-withdraw din towards our substituent. So what will happen here is we will have here a double bond, a carbon-carbon double bond between our deactivating meta director, which is our aldehyde group here. So we will have here our hydrogen, and we will have here our oxygen having a negative charge. So as you can see here, na-fill up na yung lahat ng bonding sites dun sa ating oxygen, which is actually 2. Kasi since negative sign siya, ibig sabihin, meron tayong dalawang lone pairs around dun sa oxygen natin, therefore filling up the needed sites, hindi lang pala dalawa, that will be 3. 3 sites for our bonding. So what will happen around the benzene ring? Since inagaw, by inagaw yung ibig sabihin, kulang tayo ng electron dito sa side na to. Therefore, by kulang electron, we will actually have here a positive sign or a positive charge. And since merong positive charge dyan, and due to the resonance structure within our benzene ring, that positive side can actually move around. By move around, it can move here towards that bond. Therefore, magkakaroon tayong double bond dito at double bond dito. Nandito yung positive charge natin. Maintain pa rin yung ating substituent. Again, that positive charge may attract those electrons. So, pwede siyang mag-move towards that bond. Therefore, magkakaroon tayo ng ganitong bond. And nandito yung positive natin. And nandito yung ating aldehyde group. And by moving around, pwedeng ito namang double bond about our substituent, yung mag-move back papunta ron sa ating positive charge, meaning to say, babalik tayo ron sa ating original structure ng benzaldehyde. Again, so what na naman, sir? Ano naman kung nag-move around yung positive? Kung mapapansin nyo, baliktad yung nangyayari dun sa ating activating and deactivating. Kung mapapansin nyo kanina, sa activating natin, we have there a movement or resonance structure wherein the negative charge is moved around. And for the deactivating, positive charge yung nag-move around. And Remind ko lang ulit, ano nga ulit yung pinag-uusapan natin dito? We are talking about electrophilic aromatic substitution. And as you can see here, we have positive side on the ortho side, positive on the para side, and another positive on an ortho side. So, meron kang electrophile na kung isipin natin para siyang positive charge. Siyempre, hindi siya magbabond or less yung magiging bonding towards niya sa isang positive side din. Ang ibig sabihin lang nito, for the deactivating meta-directors, anong nangyayari actually? Nagkakaroon tayo ng deactivating of our ortho and para direction kasi para orientation kasi hindi tayo magkakaroon ng bonding dyan over our deactivation of the meta orientation. Meaning to say, since mas na-deactivate yung ortho and para orientation, mas i-favor ngayon nung ating electrophilic aromatic substitution yung meta orientation. Kasi hindi masyadong or mas hindi na deactivate yung ating meta orientation. So that is how that is why we call them activating or deactivating meta directors. So meaning to say, when we talk about halogens or our benzene ring with halogen substituent, which are deactivating OrtoPara directors, it just means that our halogens are deactivating the meta orientation rather than the ortho and para direction or para orientation. So that is how the activating and deactivating. Yung explanation ng ating characterization or classification of substituent groups in our electrophilic aromatic substitution, wherein our activators or our orthopara directors are just substituents that are able to release uh, release electrons towards the benzene ring, and our deactivating meta directors are those atoms or substituents that can pull or withdraw electrons from the benzene ring, from the ring. So that is why activating and or deactivating. So in that, may bigla lang pwede kayong maisip. Paano kaya kung dalawa na yung substituents natin? So, paano kapag meron na tayong disubstituted benzenes? What will happen to our electrophilic aromatic substitution? Sige nga. Kung halimbawa dito sa first natin, we have here 4-methyl 1-nitrobenzene, and we have here this compound, hindi ko maalala kung anong tawag sa kanya, and this compound. Ano kaya? Paano kaya yung magiging orientation natin? So, ang pwede natin gawin actually class, ay i-check natin yung ating mga substituents. So, we have here our CH3. So, kung na-note nyo kung saan magpo-fall ang ating CH3, our CH3 is actually a weak ortho-para director. And as you can see here, we have here our nitro. And our nitro is actually a meta-director. So, ang titingnan natin, kung ang basis natin ay yung ating NO2, the meta for NO2 will be 1, 2, 3. So, that is one of the side. And another thing is we have here, pwede rin sa kabilang side, that is 1, 2, 3. So, that can be that side. And again, since CH3 is an ortho para director, it follows na pwedeng dito sa ortho side na to or dito sa ortho side na yan. So, by para, since occupied ng para, hindi na siya malalagyan. So meaning to say, for this disubstituted benzene, we actually have these locations for the next substituents. So how about this one? So our SO3H is actually meta director again. And our NO2 is again meta. So kung titingnan natin ang meta nitong ating SO3H, that will be 1, 2, 3. That is actually substituted na. And we have there sa kabilang side, 1, 2, 3. So pwedeng dito sa side na to. Again, same for NO2. NO2 is meta director again. So, again, pag nagbilang tayo papunta rito sa taas, 1, 2, 3, meron nang nakalagay. And next, we have 1, 2, 3. So, again, dito yung magiging attachment ng ating next na substituent. And for this last one, we have here our habang tawag dito. We have here our amide. So we have here amide, and we have here cyano or cyanic. So cyano actually is a meta director, and our amide is moderate OrtoPara director. So kung titingnan muna natin yung amide, check natin yung ortho niya. So occupied na yung isang ortho niya. And pwede siya rito, isang yan. So, yan. Lagyan natin ng isang pula. And para naman sa para niya, para ng ating amide, so we have here, tapat mo lang, pwede rin dito sa side na to. Then again, we have here a meta director. So check natin yung meta ng cyano. So we have here, palit lang tayo ng pen. So meta will be 1, 2, 3. So pwede yung side na yan. And another meta can be 1, 2, 3. So itong side na to. So as you can see here, our the next compound may be attached to this side or to this side, which is the meta, and which is this one is the ortho of our amide and meta of our cyano, and this one is the ortho of amide and meta of cyano. So that is how we go about the disubstituted benzene. Pero hindi siyempre laging ganyan ka-perfect yung mga scenario natin. Ano? Meron tayong mga pagkakataon na the directive effect or the direction effect or the orientation effect of our substituents or one of our substituents opposes the other. Meaning to say, hindi sila nagja-jive or hindi sila kakasundo kung saan ilalagay yung ano natin, yung next na substituent. So, bali ang nangyayari, in case na meron tayong ganyan, mahihirapan tayong mag-predict kung ano yung mga major products ng reaction natin. So, in that, we actually follow these rules. Wherein, for the EAS on disubstituted benzenes that are opposing groups, the prediction of the main product may be difficult. So we have here these general rules for predictions, wherein strong activating groups win out over weakly activating and deactivating groups. So by strong activating groups, that means we have there our hydroxide, our amines, our amides, and our yung mga amines natin. So basically, that can be written like this. So we have there our OH and our amines. This group will win over our ORs or yung ating mga organic derivatives of water, and also our amide, which is our NCOOH, ayan, our meal, which will win over our R groups. By R groups, yung ating aryl, and our R, it will win over halogens, which are the deactivating orthopara directors. And, syempre, lastly, yung ating meta directors. Ang ibig lang sabihin nito, class, kapag nagkataon na halimbawa, yung isang substituent, yung mga substituent mo ay opposing sila ng directive power, kung saan ipoposition yung bagong substituent. Kung ang choices mo ay in between, let's say, you have alkyl group, yung ating mga CH3, yung ating aryl group mismo, over our halogens. For example, you have here this benzene ring. Tapos meron kang CH3 dito. CH3 is our orthopara director, and the activating orthopara director naman yung ating halogens. So halimbawa ganyan, dito siya na position sa ortho na to, and you have here this chlorine. So ang ortho nito ay magiging meta ng CH3, at ang para niya ay magiging ortho ng CH3. Since magwi-win over yung CH3, hindi mo susundin yung dalawang arrows na yan, or hindi mo susundin yung sa ating chlorine. What will happen here is you will follow the CH3, wherein you will use this position, this ortho position, and this para position. Mas tama to kesa rito sa dalawang ito. Okay? So, yun yung ibig sabihin ng strongly activating groups win out over weakly activating or deactivating groups. And lastly, there is often little substitution at the position between two groups that are meta to each other. Just like our NO2 and SOOH kanina, pareha silang meta. So, minsan na nangyayari, hindi nagkakaroon ng substitution. So, that is our EAS, the EAS or electrophilic aromatic substitution for our monosubstituted benzenes and disubstituted benzenes. Actually, all of this actually holds or represents the reaction mechanisms involving benzenes. So basically, we are done with our aromatic hydrocarbons. So for the next meetings, we will be talking about alkyl halides and moving into organic derivatives of water. By my experience, for the midterms exam, I only include alkyl halides as the part of our midterms. So in that, I will be ending the video here for now. So goodbye and have a nice day.